A very warm welcome to the video lecture on the topic Smith chart and its applications. This is presented through Media Center of S College of Engineering and Technology, Tirunelveli, and it is delivered by S Sankaralingam, Department of ECE. Before we go into this topic, let us review the topics which we have covered already in the classrooms. We have discussed the basics of transmission lines. We have defined what are the primary constants and secondary constants of the transmission line. We have obtained solutions for the transmission line equations. That means we have obtained equations for voltage and current at any point along a transmission line. We have also studied the performance analysis of transmission line at radio frequencies. We made three assumptions in this analysis. One is skin effect is very much considerable, and the second one is omega n is very greater than R, and the third assumption is R is equal to 0 and G is equal to 0. Skin effect means the current flows along the skin of the conductor. That means along the outer surface of the conductor only the current is flowing, and the internal flux is 0. Therefore, we are defining the skin depth also in this case, how much depth the current can penetrate, that we have discussed in the earlier lessons. We have also discussed the input impedance of transmission line at RF frequencies after deriving the equations for voltage and current at any point along the transmission line. Now, RF transmission line means it is a dissipationless line or lossless line. Okay, here we have assumed that R0 is purely resistive. That means the load impedance is purely resistive. Now, we have also discussed in the case of lossless line a mismatched junction. When the transmission line is not terminated with its characteristic impedance, we have mismatched junction. At that junction, reflections will occur. So, along the transmission line, at any instant, there will be two wave components. One is the incident wave and the other one is reflected wave component. Okay, the incident wave travels from the source to the load, and the reflected wave, from the load it travels towards the generator. So at any point along the transmission line there will be two wave components. At some points along the transmission line, the incident wave and the reflected wave combine constructively, and they combine constructively, that means they are in phase. We get points of voltage maxima or nodes. Okay, voltage maxima are called antinodes and voltage minima are called nodes. Okay, at some points along the transmission line, the incident wave and the reflected wave will combine destructively. That means they are 180 degree out of phase, and therefore the minimum voltage will be 0 in the case of lossless line. Okay, we have also defined what is voltage standing wave ratio. Voltage standing wave ratio, we are measuring E maximum and E minimum along the transmission line. If you take the ratio between voltage maximum and voltage minimum, you will get the VSWR value. The minimum value of VSWR value will be 1. So for matched junction, the VSWR value will be unity, and for open circuit or short circuit, the VSWR value will be infinite. We also defined voltage reflection coefficient. We also discussed what is current reflection coefficient. Power reflection coefficient also we have discussed in the class. So the voltage reflection coefficient, what is the definition? voltage reflected at the load divided by incident voltage at the load. So that is the reflection coefficient. The voltage reflection coefficient maximum value is unity. When there is a full reflection, the reflection coefficient is unity, and when there is no reflection, that is when the line is terminated in its characteristic impedance, the reflection coefficient will be 0. So power reflection coefficient is the square of the voltage reflection coefficient. The reflection coefficient is denoted by the letter symbol gamma, and the voltage standing wave ratio we usually use the letter symbol S, capital S. Okay. We also discussed the relationship between VSWR and gamma. What is the relationship between VSWR and gamma? VSWR is equal to 1 plus gamma divided by 1 minus gamma. That we have already discussed. We also discussed how standing wave pattern is established in a lossless line. We have used mathematical models and calculations for solving the transmission line problems. Now we are going for one graphical method. This Smith chart is a graphical tools to solve the transmission line problems. So the Smith chart is basically an impedance chart. The lecture is organized in this manner: introduction to Smith chart, then derivation of the Smith chart, that is what is the theory behind the Smith chart, that we have to discuss, and the Smith chart, how it can be used as an impedance chart and admittance chart as well. What are the types of Smith chart we are going to discuss successively, and the properties of Smith chart are also narrated, and applications with some illustrations we are going to discuss in this video lecture session. What is a Smith chart? Smith chart was originally developed in 1939 by Smith at the Bell Laboratories, New Jersey. It is one of the most valuable pervasive graphical tool in all the microengineering problems. The chart is the reflection coefficient to impedance converter, or reflection coefficient to admittance converter, and vice versa. Okay, so the impedance values are mapped to the reflection coefficient plan. Okay, so that we will discuss elaborately in the subsequent slides. It greatly simplifies the analysis of complex design problems involving transmission lines and lumped circuits. So it is a very useful tool and is less time consuming compared to the mathematical models and calculations. Now derivation of the Smith chart, how the theory of a Smith chart is developed. We have the relationship between the impedance and the reflection coefficient, and it is given by ZL is equal to Z0 into 1 plus gamma divided by 1 minus gamma. Okay, here ZL is the load impedance and Z0 is the characteristic impedance of the transmission line. We have discussed already. Gamma is the reflection coefficient. Normalized impedance, what is meant by normalization? The impedance value will be divided by the characteristic impedance of the line. Therefore, we are getting normalized impedance. The normalized impedance Zn is equal to Z, small z we are using. Capital Z for representing the complex impedance value, and small z will be representing the complex normalized load impedance. Okay, so it is equal to 1 plus gamma divided by 1 minus gamma. Gamma is a reflection. Gamma is the reflection coefficient, and it is a complex quantity. So we can write gamma is equal to gamma r plus j gamma I. Similarly, the load impedance, it is complex. It is having both resistance part and reactance part. We are writing r plus jx. R plus jx is equal to, according to this definition, we are writing 1 plus gamma r plus j gamma I divided by 1 minus gamma r minus j gamma I. Multiplying this equation, that means we are substituting the values in the first equation. Okay, multiplying both numerator and denominator by complex conjugate of the numerator, we are getting this equation: r plus jx is equal to 1 plus gamma r plus j gamma I into 1 minus gamma r plus j gamma I divided by 1 minus gamma r the whole square plus gamma I the whole square. Now continuing the simplification, r plus jx, we are writing this equation. Okay, just expanding the term by term. Okay, separating real parts, we write r is equal to 1 minus gamma r minus gamma I the whole square divided by 1 minus gamma r the whole square plus gamma I square. Let us say this is equation number 6. So here we have taken only the real parts, so we are rewriting this equation: r into 1 minus gamma r plus gamma r into gamma I whole square. Okay, we are multiplying by r, okay, on the left side, and on the right side we are bringing the remaining terms 1 minus gamma r minus gamma I square. So on simplification we are getting this equation, just we are getting gamma r the whole square plus gamma I whole square minus 2r gamma r plus 1 plus r is equal to 1 plus r 1 plus gamma divided by 1 minus gamma. We are adding r square divided by 1 plus r square on both sides to get the complete square. That means we want to bring this equation to a standard form. Therefore we are adding this term r squared divided by 1 plus r the whole square. R squared plus ri square, that means gamma r square plus gamma I square minus 2r gamma r plus divided by 1 plus r plus r squared divided by 1 plus r the whole square is equal to 1 plus r divided by 1 minus 1 plus 1 minus r divided by 1 plus r plus r squared plus r squared into r squared divided by 1 plus r the whole square. Okay, so on simplification, after adding this term on both sides of this equation, we are getting gamma r minus r by 1 plus r the whole square plus gamma I the whole square is equal to 1 plus 1 by 1 plus r the whole square. This is a standard equation of a circle. This represents a family of circles. The center of the circle is r by 1 plus r and 0. The center is r by 1 plus r comma 0 and the radius is 1 plus 1 by r. The general equation of circle is x minus a the whole square plus y minus b the whole square is equal to c square. That is a comma b is the center and c is the radius. So in this fashion we have determined what is the radius of the r circle and what is the radius of the center of the r circle. Okay, these circles, family of circles, for each value of r we are getting one circle, and these family of circles are called constant r circles or constant resistance circles, because we are now discussing about the impedance chart. Therefore we are having constant r circles or constant resistance circles. This is the first family of a circle. Now equating the imaginary parts in the equation 5, we get x is equal to 2 gamma I divided by 1 minus gamma r the whole square minus gamma I the whole square, right? X into, so we are making cross multiplication, x into 1 minus gamma r minus 2 gamma r plus x gamma I is equal to 2 gamma I. Okay, this equation is further simplified, and we are dividing throughout by x and adding the phrase 1 plus 1 by x square. We are adding this in order to make it as a complete square. Okay, gamma r square minus 2 gamma r plus gamma I square minus 2 gamma I divided by x plus 1 by x square. That means we are adding this one plus 1 is equal to minus 1. This minus 1 is brought to the right side, minus 1 plus 1 plus 1 by x square. So we are simplifying this equation to this form: gamma r minus 1 the whole square plus gamma I minus 1 by x the whole square is equal to 1 by x square. This equation represents a circle centered at 1 by 1 comma 1 by x, and the radius is 1 by x. This family of circles are called constant reactance circles or constant x circles. So I already told you the general equation of a circle is given by x minus a whole square plus y minus b whole square is equal to c square. A comma b is the center and c is the radius of the circle. So we have obtained equations for constant resistance circles and also constant reactance circles. Now how to plot the constant r circles? It is shown here. All the constant r circles are centered on the real axis with a shrinking size as r increases. Okay, r is equal to 0. This is the circle r is equal to 0. Outermost circle of the Smith chart is the r is equal to 0. R is equal to infinity circle is reduced to 0.1 comma 0. So r is equal to 0. See, if you substitute the value r is equal to 0 here, you will get to the radius 1, okay, radius 1 by 1, that is equal to 1, and center is r by 1 plus r, that is 0.5, that is r by 1 plus r, okay. Substitute the value r is equal to 0, and what is the center, you can find out, it is 0 by something 0, okay. R is equal to infinity circle is reduced to the point 1 comma 0. So this is the radius r is equal to 0 circle. R is equal to infinity circle is reduced to this point. Here it is r is equal to infinity. So this is the plan, reflection coefficient plan. The real axis is gamma r. Real axis is given by gamma r, and the imaginary axis is gamma I. So in the reflection coefficient plan, the impedance values are mapped. So these are constant r circles. Now constant x circles are centered on a shifted line parallel to the imaginary axis by 1 unit on the right side, with a sinking edge as x increases. X is equal to 0 circle is the real axis of the Smith chart, while x is equal to plus or minus infinity circles are reduced to 1 comma 0, the point 1 comma 0. This is point 1, okay. Real part is 1 and imaginary part is 0. Real part of the reflection coefficient 1 and imaginary part is 0. So this point is x is equal to plus or minus infinity. So here we are having plus x, that is moving in the clockwise direction. The minus x, the upper half of the diagram, that is plus jx, and lower half of the diagram is minus jx. Okay, these are constant x circles. Now when these two families of circles are superimposed on a single chart, we get a Smith chart. Smith chart as impedance chart is shown here. Plotting the two families of circles, namely constant r circles and constant x circles, for all values of r and x, creates a circular chart known as a Smith chart. So just we are superimposing the constant r circles in the reflection coefficient plan, and also the constant x circles are also superimposed in the same chart. In a single chart we are getting both the families of circles. Now we have seen how the Smith chart is used as a Smith chart, the admittance chart. Now Smith chart can also be used as admittance chart. Here we are going to justify that Smith chart can be used as a admittance chart. The normalized admittance is equal to y by y naught, that is equal to g plus ib, where y naught is equal to 1 by z naught. Okay, normalized admittance is reciprocal of the normalized impedance, that is equal to y. Gamma is equal to Zn minus 1 divided by Zn plus 1, that is equal to z minus 1 divided by z plus 1, that is equal to minus y minus 1 divided by y plus 1. Okay, so we are using one transformation. What is the transformation? Gamma dash. Instead of putting gamma, we are putting gamma dash. What is the transformation? Y minus 1 divided by y plus 1. So if you are making this gamma dash, then we are getting the same result as impedance, except that the impedance plan is mapped to gamma plan, where gamma dash is equal to minus gamma. Okay, just one negative sign is appearing here. The magnitude part is the same, and the phase constant is 180 degree difference is there. Okay, this equation reveals that gamma and gamma dash have equal magnitudes, but the phase components are 180 degree apart. This fact is to be considered while using Smith chart as admittance chart. Okay. Now what are the two types of the Smith chart? We have two types of the Smith chart. One is a compressed Smith chart, another one is a standard Smith chart. Compressed Smith chart means the entire impedance plan, that is both resistance and the reactance, the entire plan is mapped 1-to-1 basis, okay, on the reflection coefficient plan. This is called compressed Smith chart. Entire Smith chart or compressed Smith chart. This includes both positive and negative parts of the impedance, that is positive real part and negative real part, that is resistance part. Okay, the entire impedance plan is mapped on a 1-to-1 basis into the reflection coefficient plan, this chart is not at all used at all. Not at all used. Okay, so this chart is known as a compressed chart, and the one which is being used is the standard Smith chart. What is the standard Smith chart? So the real part of the impedance, that is resistance part, okay, semi-infinite region, and the imaginary part in full are mapped on one-to-one basis into the reflection coefficient plan. So this is a gamma r is equal to 1 here. Okay, so I mean we can see here that constant r circles superimposed on the constant x circles. Okay, this is the standard Smith chart which we are discussing in an elaborate manner. Okay, so the radius gamma is less than or equal to 1. This is gamma. Okay, gamma is less than or equal to 1. Here it will be equal to 0. We have seen that gamma is equal to 0. That is the reflection coefficient. If it is 0, it is marked here. Now we are discussing the Smith chart properties. The constant R and constant X loci form two families of orthogonal circuits in the Smith chart. That means the two families of circles will have a 90-degree difference between them. Okay, the constant R and constant X circles all pass through the point 1, 0. That we can see all the circles pass through the point 1, 0. In the previous slide you can see all the circles, constant R circles and the constant X circles all pass through the point 1, 0. This is the point 1, 0. Okay. Now that means gamma I is equal to 0 and gamma R is equal to real part is 1 and imaginary part is 0. The upper half of the diagram represents plus Jx and the lower half of the diagram represents minus Jx. So the upper half of the diagram, this is the real axis. The upper half of the diagram means this part. Okay, this part represents plus Jx and the lower half of the diagram represents minus Jx. That means this is inductive and this is a capacitive reactance. Okay. The distance around the Smith chart is lambda by 2. If you travel the Smith chart once along its circumference, you have traveled a distance of lambda by 2. So we have seen already while studying the standing wave pattern, the impedance value, the voltage value, the current value, all repeats every half wavelength. Therefore, we have designed the Smith chart. The Smith chart is designed in such a way that the circumference distance is lambda by 2. Okay, at a point of jet, minimum is equal to 1 by S. S is equal to VSWR. S is VSWR. I told you already. There is E minimum on the line. E minimum on the line. And at a point of jet maximum is equal to S. S is equal to VSWR. There is E maximum on the line. So this can be seen in the subsequent slide also. The horizontal radius to the right side of the chart corresponds to E maximum, I minimum, jet maximum and S. We have already seen the standing wave pattern. Wherever we get a point of voltage maximum, the point corresponds to I minimum. Okay. So if I is minimum and voltage is maximum, you are getting the impedance maximum, and it is the value is VSWR. Yes, you are getting on the right side of the chart. Horizontal radius to the right of the chart corresponds to E maximum, I minimum, jet maximum and S. The horizontal radius to the left of the chart corresponds to E minimum, I minimum, jet minimum and 1 by S. Okay. The analogous to this point we are writing another point. Okay. For admittance, the constant R circles become constant G conductance circles and the constant X circles become constant B, that is susceptance circles. So we have already discussed the Smith chart. It is basically an impedance chart. It can also be used as an admittance chart. So how it can be used? The R circles become G circles and the X circles become B circles. That's it. The normalized admittance Y is a reciprocal of the normalized impedance. This we have proved already. The corresponding quantities at the admittance chart are 180 degree out of phase with those in the impedance chart. Gamma is equal to gamma minus gamma dash plan. So we are having the phase difference of 180 degree. The normalized impedance or admittance repeats every half wavelength, that is lambda by 2 distance. Normalized impedance or admittance, not only impedance though, when you say impedance, voltage also repeats every half wavelength, current also repeats every half wavelength, and impedance also, and also the admittance repeats every half wavelength. Okay. Then there are some circular scales on the Smith chart. Wavelength and degree scales are available. If you move along the transmission line towards generator, that corresponds to moving clockwise on the Smith chart. Okay. And traveling along the transmission line towards load corresponds to moving anti-clockwise on the Smith chart. This can be seen here. See, it is written here, towards generator. That means from the load we are moving towards the generator, you are moving clockwise. Okay. And when you move from the load to the source, towards load, this is towards load, from the source to the towards generator, that is from load to generator, this is clockwise, and towards load, this is anti-clockwise. Okay. Source to load. That means the incident wave is traveling in the direction from source to the load, and the reflected wave will be traveling from the load to the source. The markings for the positive and negative normalized reactances can be seen on the impedance chart close to the outermost circle. Okay. So this we can see in the impedance chart also. I have displayed the chart here. Okay. See, these are circular scales. These are circular scales along the circumference of the Smith chart. Scales are marked. Okay. And just beneath this Smith chart, below the chart, some other scales, radial scales are also. From you have to drop a line from the real axis, that is this axis. You have to drop a line and find out the values. Here voltage standing wave ratio can be measured, and also the VSWR, reflection coefficient, can also be measured, reflection loss, then reflection factor, then VSWR in dB. All these things are listed here. We can see one by one. Okay. So the circular scales, first one is we have already discussed the how when we are moving clockwise, when we are moving anti-clockwise along the chart. Okay. The positive and the negative normalized reactances we have seen. Okay. And close to the outermost circle, plus Jx minus Jx, that we have discussed. Okay. Degree scale goes through 180 degree positive and 180 degree negative, with 0 degree being on the right side, right hand semi-axis. 360 degree phase change corresponds to the reflection coefficient, corresponds to lambda by 2 wavelength. Okay, 360 degree phase is moving through 360 degree means, that means you have traveled a distance of lambda by 2. Electrical length is lambda by 2. Okay. So the reflection coefficient we have already discussed. It is a complex quantity having both magnitude and phase angle. The phase angle is marked along the degree is marked along the circumference of the Smith chart. Okay, and the magnitude part is marked along the scale available just beneath the Smith chart. The phase relationship marked in degrees and the electrical length graduated in fractional wavelength are shown on the outer edge of the Smith chart. Okay. Radial scales. A number of radially marked scales at the bottom of the Smith chart are placed in such a manner that they can be radially set off, and their values read off from the center of the chart by using a compass. Voltage reflection coefficient. that can be measured just with the scale available just beneath this chart. This scale starts from 0 at the center of the chart and ends at 1 at the outer rim of the chart. Okay, voltage reflection coefficient. The minimum value is 0 and the maximum value is 1. So it starts from the center and goes to the outer rim of the chart, maximum value. Power reflection coefficient PWR. This scale also starts from 0 at the center and ends at 1 at the outer edge of the chart. Return loss, ratio of incident power to the reflected power, return loss. Okay, at any point along the line, this scale starts from 0, gamma is equal to 1 at the outer edge of the chart and approaches infinity at the center of the chart where gamma is equal to 0. Okay, modulus of gamma is equal to 0. So return loss can also be measured, reflection coefficient can be measured, voltage reflection coefficient may be measured, power reflection coefficient could be measured, reflection loss, ratio of incident power to the difference between incident power and the reflected power. This is called a reflection loss. This definition we have seen while studying the basics of transmission lines. This scale starts from 0 at the center and approaches infinity, and as the modulus of the reflection coefficient approaches unity. Now, some more properties are there that we are discussing here. Transmission loss coefficient. Transmission loss coefficient is used as a correction factor for additional line losses created in a lossy transmission line. So this is with reference to one lossy transmission line due to high VSWR. If the VSWR value is 1, matched case, the correction factor is read out to be 1. If VSWR value increases, losses increases and correction factor is also increased. So the minimum value of VSWR is 1 and the correction factor is 1. Okay, so this is for the case of lossy line, there will be losses. Okay, 1 dB step scale, that is this is useful to calculate VSWR. Again, it is useful for the lossy line only. Voltage standing wave ratio. This scale starts from 1 at the center of the chart to infinity at the right hand margin. That means the minimum value of VSWR, voltage standing wave ratio, that is 1, and it goes to the infinity value for the short circuited case and open circuited case. Okay, VSWR is also measured in dB, so you have to take 20 log of this VSWR value, that is voltage standing wave ratio. So therefore, you will get the VSWR value in dB. Now the Smith chart is shown here. Okay, so there will be radial scales, there will be circular scales. So constant R circles, constant X circles, everything shown in a single chart. This is the composition of Smith chart. We shall now discuss some of the applications of Smith chart. The first problem is to find the input impedance of a transmission line having the characteristic impedance Z0 is equal to 50 ohms and is having the length of lambda by 8 and is connected to a load impedance of ZL is equal to 50 plus J50 ohms. That means the load value is given and we are going to find out the input impedance of the transmission line. This is the question asked. Okay, so we are going to use the Smith chart to solve this problem. We can understand how easily it can be done. What are the steps involved? They are listed here. First one is the load impedance is marked on the Smith chart. ZL is equal to given 50 plus J50 ohms. In the Smith chart you have to locate the normalized load impedance. Normalized load impedance is ZL by Z0, that is 50 plus J50 divided by 50, that is equal to 1 plus J1. This is located here. ZL is equal to, so you have to mark the intersection of the R is equal to 1 circle and X is equal to plus 1 plus J1 circle. Okay, so intersection of these two circles will give you the load impedance point. Now using this load impedance point from the center of the chart, taking this as the radius, we draw a circle. That circle is called constant VSWR circle. Constant VSWR circle is drawn. It is having the radius of the distance from the center of the chart to the load impedance point. So after drawing this constant VSWR circle, we have to now we have to move towards the generator. How much distance is to be moved? It is lambda by 8. So we want to find out the impedance at this sending end or the source impedance, input impedance is to be determined. Therefore we have to move from the load. This is the load point. From the load we have to move lambda by 8 distance. The electrical length is marked along the periphery of the Smith chart. So from the load point, so you just extrapolate this line and find out the value at this point, then move lambda by 8, that is 0.125 lambda, from that point towards generator. Towards generator we are moving, okay, from the load to the source. Towards generator we are moving lambda by 8 distance, and we are cutting at this point. That is this point is correspondingly you have to mark the input impedance. On the constant VSWR circle you find out the intersection of the constant VSWR circle and this line which you have drawn just now. Okay, so this point will give you the input impedance value. Jet input value, the normalized value is 2 minus J1. This is from the lower half of the diagram, therefore it is 2 minus J1, right? So to find out the actual impedance, you have to multiply it by the characteristic impedance of the transmission line. Jet input normalized value into 50 ohms. Therefore 2 minus J1 into 50 ohms, that is equal to 100 minus J50 ohms. This is the input impedance of the transmission line for this given problem. Okay, it's quite simple. So you have used the Smith chart to find out the input impedance of the transmission line given the value of load impedance. Load impedance value given any value of the load impedance, if it is given, then you can find out the jet input. You have to find out the jet input. Okay, input impedance of the transmission line you can find out. This is the first application of the Smith chart. Another application is, again we are going to find out the input impedance. Here the input reflection coefficient is given. Input reflection coefficient, instead of giving the load value, we are given the value of input reflection coefficient. So input reflection coefficient, reflection coefficient is a complex quantity having both real part and this imaginary part, that is phase constant. Phase value is pi and the magnitude part is gamma n. So this is marked here. Gamma input value, gamma input is given here, and the magnitude part can be read here on the radial scale. Along the circular scale we can mark the degree value of the reflection coefficient. Okay, if it is given you can mark it here, and from this point say if it is 160 degree at this point. So from this 160 to this center of the chart you draw a line, and this line will be cutting this here. So you have to extrapolate this point to the radial scale. You can find out the gamma magnitude value. Gamma magnitude value is here. So you can draw this line, and when you mark this point, okay, you can draw the constant VSWR circle also. Normalized value of resistance and reactance can be read off from the Smith chart at point A, giving jet input as Z0 into R plus Jx. So jet input value can be determined. It is Z0 into R plus Jx. R plus Jx you are reading it here. Okay. So this point is the VSWR value. Corresponding gamma value is given here. So this can be described as a constant VSWR circle also. Okay. So locate gamma in. Gamma in is equal to e raised to j pi on the Smith chart. The magnitude of gamma can be read off the reflection coefficient voltage radial scale here. reflection coefficient, voltage radial scale at the bottom of the chart, while angle value is read of the circular scale. It is here. Right, normalized values of resistance and reactance can be read off the Smith chart at point A. This is point A. It is not marked as the A, but this is the point A. So at this point you have to find out the reactance value. It is on the upper half of the diagram. Therefore it is R plus JX. So if you multiply by the characteristic impedance Z0, okay, you will get the actual impedance value. Conversely, if Z input is given, then the value of gamma, both magnitude and phase angle, can be read off from the radial and circular scales respectively. From the radial scale you will read the magnitude part of the reflection coefficient, and from the circular scale you will read the phase angle of the reflection coefficient. So this is the problem described here in this application 2. ZL is the load impedance, and this is the load point. We are finding the Z input. Okay, so sending and input voltage we are sending, and input impedance we are determining. Okay, given the value of input reflection coefficient. The next application number 3, find the admittance value for an impedance value of Z is equal to 50 plus J50 ohms in a 50 ohm system. That means we are trying to use the Smith chart as the admittance chart. So we are going to find out the admittance. The impedance value is given 50 plus J50. So it is to be marked along the Smith chart. Z0 is equal to 50 ohms. It is given. The characteristic impedance of the transmission line. Since we are going to find out the admittance value, we are finding out the normalized admittance. Normalized admittance is 1 by 50, that is equal to 0.02 ohms. Locate ZL normalized. ZL normalized is 1 plus J1, because it is given 50 plus J50. If you divide by 50, you will get 1 plus J1 on the Smith chart. Now, so this is the ZN value. So point A is marked here, and then you have to draw the constant VSWR circle. Okay, move 180 degree from this point to the other part of the diagram. You will get this point. Okay, this point is the reciprocal of this impedance value, that is admittance. The admittance, this is the input admittance of the transmission line. That is, we are reading it as 0.5 minus J0.5. Okay, so this is at the lower half of the diagram. So you will read it as minus J0.5. 0.5, the constant R circle. Here you will say that it is a constant G circle, okay, conductance circle, and this is a susceptance circle. 0.5 minus J0.5. So intersection of a constant G circle and a constant B circle, you will get the input admittance. So normalized input admittance you have read, and you can find out the real value of admittance. So real value of admittance, the normalized value into the characteristic admittance, that is 0.02 mho. So 0.01 minus J0.01 mho. Okay, so this is the admittance value. So impedance value is converted to admittance value using the Smith chart. Now in this application number 4, we are going to find out Z maximum, Z minimum and their positions. At what position the maximum value of the impedance appears, and at what value the minimum value of impedance occurs. So this we are going to determine in this problem. A transmission line is given, load value is 100 ohms, load value 100 ohms. The transmission line length is marked as L. Characteristic impedance of the line is 50 ohms. Okay, so the distance between any two successive minima, this is one minimum, this is another minimum, the distance is lambda by 2. Okay, the distance between one minimum and the subsequent maximum is lambda by 4. It is marked here. Now coming to the problem, we will read out the problem. A microwave signal is traveling on a transmission line that has a characteristic impedance of 50 ohms, right, and a load value of 100 ohms. It is given here 100 ohms resistive load. Okay, Z0 is equal to 50 ohms. find the values of jet maximum and jet minimum and their locations on the line. Okay, because RL is greater than jet naught or R naught. Okay, characteristic impedance of the, so interchangeably we can use jet naught and R naught for the case of lossless line. Okay, jet naught is equal to 50 ohms. You can also write R naught is equal to 50 ohms. Okay, because RL is greater than R naught, the maximum voltage and thus maximum impedance occurs at the load itself. So at the load point you are getting maximum. This we have already proved during the mathematical calculations. Jet maximum is equal to jet L is equal to 100 ohms in this case. Okay, so it is given because jet L is greater than jet naught. Okay, so maximum impedance is appearing or occurring at the load point itself. So jet maximum normalized value is equal to 100 minus 50, that is equal to 2. Okay, so similarly L maximum, what is L maximum? L maximum is the distance from the load to the maximum point. So since the maximum appears at the load itself, L maximum is equal to 0. Okay, the minimum impedance occurs lambda by 4 away from the load, the next minimum. So lambda by 4 distance away from the load. Okay, so L minimum is equal to lambda by 4. L minimum is equal to lambda by 4. Therefore jet minimum normalized is equal to 1 by jet maximum normalized. 1 by jet maximum normalized, that is equal to 50 by 100. Okay, you have to come to this point. Okay, this is that means I have travelled lambda by 4 distance. So how much distance is to be travelled? Lambda by 4 distance. If you go around the Smith chart once, it is lambda by 2. If you go for the halfway, it is lambda by 4. So jet minimum normalized is equal to 1 by jet maximum normalized, that is equal to 50 by 100. Jet minimum is equal to 50 by 100 into 50. The actual value is 50 by 100 into 50, that is equal to 25 ohms. So we have determined jet maximum, jet minimum and their positions also. So position is, this is at a distance of lambda by 4. At a distance of lambda by 4, the minimum occurs. Maximum, first maximum occurs at the load point itself. First minima appears at the distance of lambda by 4 from the load. Okay, then the subsequent maxima occurs at this point only again. Okay, this is the maximum point. So you have travelled lambda by 2 distance. Okay, so this is the input point, therefore we are marking it as jet input. Okay, jet minimum is equal to 25 ohms. Jet maximum 100 ohms, it is given in the problem itself, because jet maximum is the load impedance value itself. So this is one application. So the value of jet maximum, the value of jet minimum and the corresponding locations along the transmission line are determined in this application. The next application, again the same pattern is employed here. Here the load impedance is less than the characteristic impedance, that is the difference. So if this is the case, if the load impedance is less than the characteristic impedance of the transmission line, then jet minimum will be appearing here at the load itself. So just vice versa. Okay, because RL is less than R naught, the minimum voltage and thus minimum impedance occurs at the load, that is jet minimum is equal to, jet L is equal to 20 ohms. Okay, at the load point the given value of the load impedance is 20 ohm. So jet minimum is equal to 20 ohms and jet minimum normalized will be 20 by 50, that is equal to you can find out, so 2 by 5 ohms. Okay, L minimum is equal to 0, that means the minimum value, jet minimum is here. So L minimum, the length L represents the small l represents the length, capital L represents the load. So L minimum is equal to 0, right? So minimum value of the impedance is determined and its position is also determined, right? The maximum impedance occurs lambda by 4 away from the load. Maximum impedance, again the same concept, Okay, so you have to travel a distance of lambda by 4. So to get this value, you have to travel lambda by 4 distance. Here, L maximum is equal to lambda by 4. Yeah, lambda is c by f. C is the frequency, c is the velocity of electromagnetic wave and f is the frequency. So that into 1 by 4. Okay, lambda is equal to c by f and it is to be divided by 4. That is equal to 30 centimeter. Okay, lambda by 4. So, because the frequency is given here, 1 gigahertz. Frequency is given, therefore you are substituting c is equal to 3 into 10 raised to 8 meter per second and f is equal to 1 gigahertz 1 into 10 raised to 9. So you will get 30 centimeter, right? So jet maximum normalized is equal to 1 by jet minimum normalized. So just to take the reciprocal, they are 180 degree out of phase, therefore you take the reciprocal of this one. 1 by jet maximum n is equal to 50 by 20. So jet minimum is equal to, it is to be multiplied by 50 again, therefore you will get 125 ohms. So jet minimum value is determined, so its position is also determined, then jet maximum value is also given and jet maximum position is also determined. Okay, this is the input impedance, the source end, this is load end. Okay, characteristic impedance of the transmission line is 50 ohms. So positions of jet maximum and jet minimum are marked in the standing wave pattern. So this axis is the length. Okay, you can mark it as S. S is equal to 0, that is from the load only we are marking the distance. So it is travelled minus 7.5 centimeters. Okay, x is measured in centimeters, lambda by 4 distance. So again this is if you move another lambda by 4 distance, you will reach this point minus 15 centimeters. So this is minus L. Since we are moving from the load towards the source, we are putting it as minus L, that's all, right? So this is one application of the Smith chart. There are two methods to determine the VSWR using a known load. ZL value will be given or gamma L value will be given. So in the method 1, so ZL value will be given. So models of gamma L as the radius, gamma L you have to mark it here, gamma L. Okay, models of gamma value you have to read from the radial scale. Okay, a constant VSWR circle is drawn. Constant VSWR. So now our aim is to determine the VSWR. So gamma value is given. Once gamma value is given, it is VSWR is equal to 1 plus gamma divided by 1 minus gamma. Mathematically we can determine. Similarly, using the Smith chart also, we are now trying to find out the VSWR value. This value corresponds to the reflection coefficient value, magnitude part we are determining here. Then draw the VSWR circle, constant VSWR circle. Then from this point, if you are extrapolating one line to the VSWR scale, you will read the VSWR value. VSWR value is marked both in dB and as a ratio. Okay, so this is infinity. VSWR value starts from 1 at the center of the chart and it ends with infinity at the outer edge of this Smith chart that we have discussed already, that is marked here, right? So in the first method, gamma L is given and we are determining the VSWR value either in dB value or as a ratio, right? In the method 2, we can measure VSWR here itself. Okay, so the VSWR value can be read off from the VSWR circle intersection with the horizontal semi-axis at theta is equal to 0 degree. So right hand real axis will be corresponding to jet maximum, I minimum, then E maximum. We already discussed. This is corresponding to the VSWR value. Left side we will have jet minimum. Jet minimum means I maximum then minimum. Okay, E minimum. So you will get a minimum value of Z here. You will get the 1 by VSWR here. Okay, 1 by S. Here you will get S value. So that we can mark directly using this constant VSWR circle. Okay, so these are the two methods. From here you can either read from the radial scale or you can read from the constant VSWR circle. Here if you find out the value of the circle, the value, this point, if you take the value, it will be VSWR on the real axis of the Smith chart. So these are the two methods available for the determination of VSWR given the load value. Another application similar to the previous application of determining jet maximum, jet minimum at their positions, etc. Here also we are having one typical problem, determining the standing wave pattern. We are plotting the standing wave pattern. There also we have plotted standing wave pattern. Now exclusively we are asked to plot the radiation pattern for this particular case. That means the standing wave pattern is to be determined on a transmission line, Z0 is equal to 50 ohms, and it is terminated in the load impedance 100 plus J100 with the incident voltage E incident is equal to 1 angle 0 degree as shown in the figure. This is the problem description. Transmission line circuit diagram for the given problem is given here. This is the load value 100 plus J100 ohms. The characteristic impedance of the transmission line is 50 ohms. The E plus represents the incident wave and it travels from the source to the load. The reflected wave, because of the impedance mismatch, it is the part of the incident energy is reflected back, therefore you are getting reflected wave E minus, right. So the incident wave is having the magnitude 1 angle 0 degree, right. The solution for the given problem is given here. We need to find out E maximum, E minimum, I maximum, I minimum and their positions, Z maximum, Z minimum, VSWR. So modulus of gamma we have to find out VSWR. All these points we have to determine using the Smith chart. The solution is given here. ZL is equal to 100 plus J100. Okay, ZL normalized value is determined now 100 plus J100 divided by 50 characteristic impedance of the transmission line, that is equal to 2 plus J2. This impedance value is marked along the Smith chart. ZL normalized is marked along the Smith chart. We are drawing the constant VSWR circle and from this chart we can read out the value of VSWR. VSWR is equal to 4.4 at the point of Z maximum. See here we are reading the VSWR value. Okay, the corresponding gamma value is marked as 0.63. Gamma L modulus value is 0.63. VSWR value it is 4.4. It will be read here. It is the point of Z maximum, right. So VSWR S value will be 4.4. Gamma L is equal to VSWR minus 1 divided by VSWR plus 1. That is equal to 4.4 minus 1 divided by 4.4 plus 1. See, once the gamma value is determined, it is 0.63. It can also be directly read from the chart. It is given here. Gamma is equal to 0.63. Okay. So Z0 is equal to R0 is equal to 50 ohms. It is given. Z maximum is the point of maximum impedance. Maximum impedance is R0 into S. This we have already discussed while studying the standing wave pattern. E maximum by I minimum. E maximum by I minimum is equal to Z maximum. So therefore R0 into S, 50 into 4.4, that is 220 ohms. Z maximum is 220 ohms and Z minimum R0 by S. This also we have proved already while studying the power flow along the transmission line. We have determined all these quantities: E maximum, E minimum, I maximum, I minimum. All these quantities, if you are able to measure along the transmission line, you can find out the power flow, Z maximum, Z minimum. All these 6 quantities are required to find out the average power that is flowing through the transmission line. So we are using those formula here. Jet minimum is equal to R naught by S, that is equal to 15 divided by 4.4, that is equal to 11.36. Okay, L maximum, this can be read off from the chart. L maximum, this is jet maximum, so L maximum is to be determined. This is jet L, this is jet L, so maximum value of impedance is here. So from the load to the jet maximum point, what is the distance, electrical distance, that value is marked as L maximum. So L minimum, you have to add lambda by 4 to this value, right? So that is the concept. Therefore we are writing it here, L maximum is equal to 0.292, it is here, 0.292 is read here, and for simplification it is not marked here, 0.292, and this is 0.25, so starts from 0, this value will be 0.25, and if you travel again lambda by 4 distance, it is 0.5, so 0.292 minus 0.25, that is equal to 0.042 lambda. This is L maximum. Okay, on the right side of the real axis we have noted this value. Right on the left side we are marking it as L minimum is equal to 0.042 lambda plus lambda by 4. If you move again lambda by 4 distance, you will get L minimum value, L minimum point, okay, length, you will determine it is again 0.292 lambda. E maximum, what is E maximum? E maximum you have to determine. E maximum is equal to incident voltage plus reflected voltage, that we have discussed as already. The incident voltage and reflected voltage, they combine constructively. Okay, the phase angle between these two will be 0, and therefore you will get points of voltage maximum, E maximum. So this is the principle that we are studying while discussing the standing wave pattern. E maximum is equal to incident voltage E incident plus reflected voltage E reflected. So E reflected is equal to E gamma L into E incident. This is gamma L into gamma L is what? Reflected voltage divided by incident voltage. Okay, voltage reflected at the load divided by voltage incident at the load, that is gamma L. So if it is multiplied by E incident, you will get reflected by how much power is reflected back. So 0.63 into incident voltage is given in the problem. It is 1 volt angle degree, angle is 0, so the magnitude part is 1. So 0.63 into 1, that is equal to 0.63 volts. So this is reflected voltage. Incident voltage is 1. So E maximum is equal to incident voltage plus reflected voltage 1 plus 0.63, that is equal to 1.63 volts. Right? So E reflected value is 0.63 volts and E incident is 1 volt. So if you add these two, you will get E maximum. Point of voltage maximum 1.63 volts. So on the right side you will get the points of voltage maxima. Voltage maxima. Along the left side of the real axis you will get the voltage minima. So standing wave pattern is drawn in the next slide, I think. Yes, you will see. Then E minimum is equal to incident voltage minus E reflected, that is the minimum value. The incident voltage and the reflected voltage, they combine destructively. Phase difference is 180 degrees. So we have to deduct the reflected voltage from the incident voltage. So 1 minus 0.63, that's equal to 0.37 volts is the E minimum voltage. E minimum. So it is marked here. This is the given problem. The load value is 100 plus J 100 ohms. The characteristic impedance of the transmission line is 50 ohms. This is the source end. Okay, it is not marked, therefore standing wave pattern is extrapolated here. Right. So this is the standing wave pattern. This is voltage standing wave pattern. This refers to the current reflection coefficient. Current reflection. That means current reflection plus current wave. The incident wave and reflected wave when you are considering the current values, we are marking the standing wave pattern, current standing wave pattern. Okay, voltage reflection coefficient maximum value we have determined, it is 1.63. It is given here 1.63 maximum voltage 1.63. It is marked here 1.63, right? And the minimum value is 0.37. It is 0.37 volts. L minimum, it is from the load, it is 0.042. So this much distance is given here. The value of voltage at this point is not known here now. Okay, so the voltage maximum is appearing at a distance of 0.042 lambda from the load. So that is the concept here. And if you are adding lambda by 4 distance, again you will get the successive minima, sorry, 0.292 lambda. Okay, so this is the minimum point, voltage minimum. This is voltage maximum. Voltage maximum value is 1.63 volts. Voltage minimum value is 0.37 volts. Okay, so this plot is understood now. You can put X or S. In some standard textbooks they will use S. S, small s represents the distance from the load. Here the centimeter scale is written in X. Now I maximum and I minimum are to be determined. What is I maximum? E minimum divided by Z minimum. Okay, you will get I maximum. E minimum divided by Z minimum. That means 0.37 volts divided by Z minimum, that is 11.36. That is equal to 32.6 milliampere. Okay, so you can calculate this 0.37 volts. 11.36 is the Z minimum. Z minimum is 11.36 ohms. So you will get the value 32.6 milliampere. Okay. Similarly, I minimum is equal to current minimum E maximum by Z maximum. That will be current minimum. E maximum point at the point of voltage maximum, you will read 1.63 volts. Okay, 1.63 volts divided by, see, wherever you get E maximum, you will get current minimum. This is the principle involved in the standing wave pattern. At a point of voltage maxima, it by default refers to voltage current minimum. Okay, voltage maximum corresponds to voltage minimum. Similarly, voltage minimum corresponds to current maximum at that point. So you have to make sure that symmetry is maintained while drawing this standing wave pattern. Okay, I minimum is equal to E maximum by Z maximum 1.63 divided by 220 volts. That is equal to 7.4 milliampere. So you are marking it here. So this is 7.4. This is the minimum value of current. Maximum value of current is 32.6 milliampere. Now the current standing wave pattern is plotted like this. Okay. Final standing wave pattern is shown here. This is voltage standing wave pattern. This is current standing wave pattern. It is marked in milliampere current value. Voltage is marked in volts, and the distance is measured in say it is electrical distance, or you can say that it is measured in centimeters. So lambda value, if you substitute, you will get the actual value of the, that means the physical length value you will get. So in this way we are determining the E maximum, E minimum, I maximum, I minimum, Z maximum, Z minimum, the positions of these parameters, and the VSWR value, gamma value, everything we can determine using this Smith chart without going for tedious mathematical calculations. Simply by using the chart we can find out all these quantities. So there are some more applications which we can see in the next video session. Thank you for patiently watching and hearing this video lecture. Thank you very much.